Hi, welcome back to C23 Classroom channel. Today we would like to discuss about boundary layers and how to solve boundary layers problem with von Karman equation. So let's say we have question of determine the boundary layer thickness and drag coefficient in laminar boundary layers that have second order polynomial velocity profile. So from this question, what you need to understand is you need to define or you need to derive what is the equation for boundary layer thickness and what is the value of drag coefficient for laminar boundary layer that have velocity profile of second order polynomial. So why boundary layer thickness equation becomes an important parameter here? It is because, as we discussed previously, we only know that delta is equal of y at u local velocity equal to 99% of free stream velocity. It is mean that we don't know what is the value of delta and we also don't know what is the value of y. So it makes our calculation difficult here. From this equation only, it means that we need to measure the boundary layer thickness from experimental works. Okay, so to solve this problem, we need to use von Karman equation. So if you still remember, von Karman equation is equation that have tau, shear stress. Why shear stress is become an important parameter? It is because if we see the equation of drag force here, we found that drag force is the summation of force in x direction. So means that we have summation of force that comes from the different pressure and force that comes with because of the existence of shear stress. If we see this equation, we found that pressure can be measured directly. Usually people could measure pressure by put a pitot-static tube probably in flat surface, and then we could measure the pressure on the surface. Cos theta can be measured. We can measure the inclination of that surface. A is the area for sure. We have a flat plate, and then we could measure the area of flat plate. But the shear stress that occur on that surface is unmeasurable directly. So we need a calculation, a numerical, to calculate what is the value of tau. Then by having that answer, we could solve this equation, and finally we could get what is the total drag force in our system. Okay, as the answer for that question, it stated there the velocity profile is polynomial. So it is means that our u over u, our velocity profile here is by the power of 2. So as we done previously, we could prove that polynomial velocity profile can be written as u over u 2 y over delta minus y delta by square. So and then please remember the von Karman equation, tau equal rho u square d theta over dx. And then another shear stress equation that comes from Newton's law of viscosity. So it is tau equal to mu du dy at y equal to 0. You need to remember this condition. Then to solve this problem, we start with von Karman equation here. So in von Karman equation, we have theta here means we need to find what is the value or what is the answer for momentum thickness for this velocity profile. So the equation for theta is here. We already learned about this previously, and I hope you could substitute the value of u over u in this equation, and then you could do the integral process, and finally you will get that theta for this velocity profile is equal to 2 over 15 delta. So what you need to do is you substitute the value of theta here with 2 over 15 delta. And then sometimes might be you have difficulty to do this one. It is better for you to think that just separate the d dx here and then put a bracket here, and then you put the value of theta, which is 2 over 15 delta, and then you assume that this equation is equation number 1. Okay, next step is we need to do simultaneous solution. So we use another term of shear stress, which come from Newton's law of viscosity, so which is mu du dy at y equal to 0. So what you need to do is we need to find first what is the value of du dy. We know that u over u is 2y over delta minus y over delta square. So we replace the u here to the right side, so we have this term, and then we could differentiate u to the y here. So from this equation, we found that du dy is equal to 2u over delta minus 2uy over delta square. And then this is a compulsory step. We need to come with the value of du dy at y equal to 0. So what we need to do is we substitute the value of 0 in y terms here, and finally we could get that du dy at y equal to 0 is equal to 2u over delta. Then this is the equation of Newton viscosity law, and then we substitute the value of du dy at y equal to 0 with 2u over delta, and we state this equation as equation number 2. Next, what we need to do is we equalize both function of shear stress. So this is the equation from von Karman equation, and this is equation for Newton viscosity law. So we equalize both of them, and our aim, our objective is to find what is the value of delta. So what we need to do is we simplify everything here, and then we put delta and d delta in the left side, and put all the terms here in your right side. So finally you could write as delta d delta is equal to 15 mu over rho u dx. So mu here is the dynamic viscosity, rho is the density, and u is the free stream velocity. And to have delta here, what we need to do is we integrate both sides. So we integrate delta to d delta, so we will get delta square over 2, and then integration of 15 mu over rho u to dx, so we have 15 mu over rho u x plus c. So c is the constant value. So we assume that at this origin, at the first point of flat plate, which is x is equal to 0, on that point, the boundary layer thickness still not developed, so we assume that delta is equal to 0, so it makes c constant is equal to 0. After we determine this one, we could say that the value of c here is equal to 0. So finally, we could say that delta square over 2 is equal to 15 mu x over rho u. After that, we need to simplify this equation. Then we bring all the parameters to the right side. So we have 30 mu x over rho u. And then we must have the common way is we must to show the value of delta here in terms of Reynolds number. So what we need to do is Reynolds number is rho u x over mu. However, in this term, we find that the x is at the top. So what we need to do is we just multiplying x over x here. So it equal to 1. So means that our terms here is still remain the same value. So we could write that rho ux will become rho ux here. So mu is remain as mu, and 30x here will become 30x squared because we have another x at this portion. So and then we from delta square we make it as a delta, so it's become root 30x squared over Real number, and finally we could say that delta is equal to 5.48x over root Real number. So this is the equation to find the thickness of boundary layer thickness for second order polynomial profile. How to use or how to calculate the boundary layer thickness using this equation. Let's say we have one condition like this. We have a thin flat plate here, and we have, let's say, a water flow from left to the right and create the boundary layer thickness on the flat surface. So let's say we want to calculate what is the boundary layer thickness at point 1. First, what we need to do is we need to know what is the location or the coordinates for point number 1. Let's say for point number 1 here, so the distance from the origin here is 0.4 meter, and we assume that the fluid here is water, means that the density is 1000 kilogram per meter cube, and the mu, the dynamic viscosity of water, can be simplified into 0.001 Pascal second, and we assume that this water flows at u free stream velocity 0.2 meter per second. So what we need to do is we use all of these data and substitute into this equation. So we know that delta is equal 5.48x over Real number here. So we substitute the value of x with 0.4, and then we change the Real number terms here into its equation, which is rho ux over mu. We substitute all the parameter here, which is rho is the density, u is the free stream velocity, x is the location of point 1, means that the value of x here is same as this x, and this is the mu, the dynamic viscosity, and we could say that the delta is 7.75 times 10 by the power of minus 3 meters. Please remember that boundary layer thickness here is distant from surface here to the location where the local velocity is 99% compared to the free stream velocity. It is mean the distance here we could measure it with unit of meter. Next, we need to calculate what is shear stress occur for the velocity profile of polynomial velocity profile. So previously we already know that we have two equations for shear stress. One is tau equal mu 2u over delta, which come from the Newton law of viscosity, and tau equal rho u square d theta dx, which come from the von Karman equation. So from these two equations, to calculate shear stress, I advise you to use equation from Newton's law of viscosity. It is because in Newton's law of viscosity, the value of tau here is fully developed. So if we see terms from von Karman equation, it is rho u square d theta dx. The term difference of d theta over dx here showing that this equation is not fully developed. It is mean that we cannot use this equation for further investigation. So please remember, use the shear stress equation from Newton's law of viscosity. So what we need to do is we substitute the value of delta from our previous answer here, which is delta is equal to 5.48x over Reynolds number, and then we could get that tau is equal 0.365 mu u over x and Reynolds number. Please be advised that the value of delta equal 5.48x over Reynolds number here is only for velocity profile parabolic profile. For another velocity profile, the delta here needs to be calculated again, and the value is not 5.48x over Reynolds number. Next, we are going to calculate these two items, local drag coefficient and drag coefficient. So local drag coefficient usually symbol as C subscript small d, and drag coefficient is C subscript capital D. So the difference between local drag coefficient and drag coefficient is local drag coefficient is drag coefficient that occur for one local point. For example, we have point 1 here. So the calculation is only for this point. The drag coefficient for only this one point is called local drag coefficient. And drag coefficient here is the total drag coefficient for the whole object here. Please be advised that for calculation of drag coefficient here, the influence of area must be included in your calculation. I will show you later. Okay, let's go for local drag coefficient CD. As we know in previous calculation, tau is 0.365 mu u over x Reynolds number here, and we know that from the common equation tau for local drag coefficient, tau is equal to CD 1 over 2 rho u squared. So if you see here, so this equation is actually similar with the common equation of drag force is equal to CD times 1 over 2 rho AU squared. As I said previously, local here means the calculation is based on one single point. So the value of A here is not exist in this equation. So we have two equations of shear stress here. What we need to do is we equalize these two equations, these two value of shear stress, and then we could simplify the value of CD is equal to 0.73 over third Reynolds number. Please try this at home. For drag force, as we know that force can be calculated by multiplying shear stress and area. So what we do here is we do the integral process of shear stress times B times dx. B is width of our thin flat plate and dx is the length in x-axis. So B times dx will represent the value of area. So tau A could give us force. The integral limit is from 0 to L. So 0 is the origin and L is the maximum length of our flat plate. We substitute the value of tau that we get in previous slide. So this is the value of shear stress that we get, and B is the width and dx is the distance in x-axis. We replace the value of Re with its common equation, which is rho ux over mu, and then we simplify this equation. We have two terms of x here, 2 mu and u here, so we could simplify it into these terms. We do the integral process from limit 0 to L, and finally we could say that drag force can be calculated by using this term, which is 0.73 times u cert rho u mu, cert L, and B. And this is the calculation for drag coefficient. Previously in our slide, we know that drag force is equal to CD 1 over 2 rho A U square. So we rearrange this equation, so we have 2 times FD over rho A U square, and we know that A is length times width, and we could say we substitute the value of FD that we get from the previous slide, so we could write CD is equal to this. And then we simplify this term, and finally we try to represent Reynolds number, and we could get that CD is equal to 1.46 over third Reynolds number. So here, because we are calculating a flat plate, so instead of we are using rho ux, we could use rho ul, which is L is the length of our plate. Normally, we could say that 0 is the origin of our plate and L is the maximum value or the maximum length of our flat plate. Okay, for your tutorial, I hope you could do by yourself at home to find delta, boundary layer thickness, CD, local drag coefficient, and local coefficient, C capital D here, for all velocity profile. What I showed you previously is the calculation for delta CD here for parabolic profile, means for u over u 2y over delta minus uy over delta square. And the answer is 5.48x over Reynolds number, 0.730 over Reynolds number, and 1.46 over third Reynolds number here. So I hope you could try at home to get the value of delta and CD for the velocity profile of this and other type of velocity profile. Then here I show you one answer for Blasius exact solution. So I will explain about this in my next presentation. Please subscribe this channel, C23 Classroom channel. Thank you for watching.